So today we are delighted to welcome Dr. Paxon Frady, who has traveled back to the Bay to visit us today. Paxon received his bachelor's at Caltech in computational neural systems, as well as business, economics, and management. Paxon did his PhD in neuroscience at UC San Diego, producing a thesis with the intriguing title of Activity Mapping the Leech Nervous System, in which he details biophysical models of population encoding, experimental techniques, and computational algorithms to understand neural computation. For postdoc, Paxon moved upstate and down the hill to UC Berkeley's Redwood Center for Theoretical Neuroscience, and there collaborated with many of us here at the lab in projects involving neuromorphic and hyperdimensional computing and its application in machine learning. Currently, he is a research scientist in the neuromorphic computing lab at Intel, and it is on his work there that he will be speaking to us about today. So welcome, Paxon.
All right. Okay, well, yes, I'm Paxon, and yes, I work for the neuromorphic computing lab at Intel, and yes, today I'm going to be telling you a bit about our neuromorphic computing chip, Loihi, as well as a bit of my research and the kind of problems we're interested in tackling and what's promising about neuromorphic computing. So, of course, you know, I might be talking about Intel hardware, but just don't sue Intel, basically. But neuromorphic computing, of course, is inspired from the brain, and what we see from even simple nervous systems out there are just incredible computational abilities packaged in animal brains, and they operate also at extremely low power, and as well as like have these amazing abilities of perception and agile flight. And compared to our modern computer architectures, there's still a lot to learn about how the brain works and how it's capable of producing these amazing feats like just behavior and learning and all these amazing things that brains do. And so our team at Intel was, of course, originally computer architectures, but they decided to look at neural computation and computational neuroscience to get some inspiration in a new type of computer chip architecture. And so the entire field has been exploring alternative ideas about how to make computers based on things we know about neuroscience in the brain. And so we've been putting effort into mimicking a lot of the properties of brains and incorporating them into these new types of chips. And kind of the main insights that we've incorporated into the chips are really about keeping compute and memory co-localized, using asynchronous computing, and communicating with spikes or events. And this has led to a lot of promise in the field. And of course, the field at large is also exploring very exotic things like resistive RAM and alternative types of device hardware. But our chip at Intel is still very conventional in the sense of it's just normal transistors, using Intel's normal fabrication process, but just the architecture is just trying to include a lot of these new insights from neuroscience, as well as learning algorithms. And so compared to kind of the normal computer architectures out there, there's kind of now these two main paradigms of just our conventional CPUs that we are used to and sequential algorithms and programming. But now also, like with the rise of AI and deep learning, there's a lot of efforts into just making more and more kind of advanced versions of graphics processing units, since deep learning sort of is really well optimized to those types of architectures. But what we can do then with neuromorphic computing is quite different than kind of conventional deep learning architectures, and the hardware is designed for different purposes, and we're still in a way kind of trying to find the niche for applications of the hardware, but we think there's a lot of promise in how you can use asynchronous spiking and on-chip learning rules and sparse computations to find new applications for these computer architectures. And compared to kind of modern AI, the neuromorphic hardware really excels in just the low power. So one of the biggest, I think, benefits of our hardware is actually just doing things really efficiently and having the flexibility of doing learning algorithms and other things in a very efficient manner. So at Intel, we have, of course, a lot of threads about the hardware itself, and the founders of our team were experts in just asynchronous computing, and so they have a lot of innovations in just asynchronous computing designs, and that's sort of the foundation of our neuromorphic hardware. And a few years ago, we came out with the first neuromorphic chip, Loihi 1, but more recently, there's this new version of it, Loihi 2. And this has a lot of new features over Loihi 1. Just it's larger, it's faster, it has these graded spikes and more flexible learning rule, more flexible programming model for making different types of neurons. And but then as well, the chip has these variations in form factors where the design of the chip is such that you can create a large mesh of them and scale up the entire architecture to build, very, very large systems. And so we have a couple of different variations of these systems. So there's this 8-chip kind of system that we use in our INRC cloud that people typically will have access to. But then we have a small form factor, which is about the size of a USB stick and has 2 chips on it, as well as then we built systems that are about the size of a server rack, which have hundreds of chips on them. And currently we're working on building like another server rack system that can simulate almost 1 billion neurons. And so then the mesh is like very powerful way to create these large scale architectures and utilize the computer architecture for scaling up. And then we've also been working on software. So one of the things about the whole paradigm of neuromorphic computing is that it is quite different than conventional computing. And one of the main things that is different is that you communicate with these spikes, but they're also kind of transient. And so you have to kind of think about your network architecture and how it behaves and plan a little bit ahead about what you want the network to do and how to access memory or keep things around and deal with timing. And so we've been working on a whole software stack to help people design algorithms and think about how to program on the chip. But there's still a lot of, I think, just ideas at the software level that we need to flesh out to make it easier to program on these things. And then, of course, our team has been developing lots of different types of applications. We've sent some Loihis to space, but then we've also been working on some optimization algorithms for things like satellite routing, and of course, a lot of new things for robotics and perception, and some other things I'll tell you about later. So as well, Intel has the Intel Neuromorphic Research Community. So this is our academic partnership with, our partnership with academic collaborators. And basically, we give out some grants, but mostly it is just to let people have access to the chip. So basically, if you do want to work on Loihi 2 and try out some algorithms, you can pretty much send us a small proposal and sign an NDA, and then we'll give you access to our servers, which have the chips, and you can work on it there. And so then we also have little workshops and training events twice a year, and just trying to grow the community and get people finding good applications. And so So then Loihi 2 itself is um, made on Intel's like kind of new fab, the Intel 4 technology. And we break the chip down into what we call neurocores. And so there's 120 neurocores on a single chip. And each of these kind of has its own localized program memory, uh, and then the cores kind of communicate through this neuromorphic mesh. And basically, we send packets. We like to call them spikes, but they're not quite like spikes like the brain, but they're more like Ethernet packets. And you then communicate through the cores by routing these packets around. And so the chip has about the ability to simulate 1 million neurons, but in this new version of the architecture, you can create pretty complicated neuron models with a flexible programming language. And depending on how complicated your neuron is, you're going to use up more and more resources. So for the simplest neurons, you can get up to 1 million, and then maybe 100 million synapses. And the synapses here are based on this address event routing schema that's very common in the field, where instead of creating like a fixed matrix that can't really scale, the system uses the addresses to route more arbitrary synaptic connectivity around. And so then you can make much more complicated network graphs, but again, there's still like a limit in terms of the amount of memory you have access to. And then, we have this mesh, and we're working on some other exotic ideas like scaling it in 3D, and also still working on optimizing the input and output, streaming data in and getting outputs. The newest version of the chip has a Ethernet connection that can accelerate our input and outputs, and then there are also a couple of kind of conventional CPUs on the chip that help you program it and can do some minor, control systems for monitoring the chip or setting up the chip in certain ways. And then we have a programming language that we call Lava. This is our software, and the main idea of Lava is to provide a generic interface for general neuromorphic devices. And so we have these parallel kind of implementations of all of the things that you can run on the chip that can be also run on other backends. And so it's a useful way to abstract away the algorithms and also to kind of test the algorithms onto the CPU and make sure like things are working on the chip. And it's open source, and still like developing some of the conventions for using the chip through this software Lava. And so then basically, the abstraction layers we use in the software are generally to build on these processes, these neural processes. And so typically we define something like an integrated fire neuron as a process, or we can define more complicated neuron models like these resonating fire neurons or Isakevich neurons, or there's actually a lot of flexibility, but then we kind of package this up into a process, which is one of the reusable components. And then we have this recursive system for then building little network motifs. So you might want to, build some component for your application and then package it up into this hierarchical composition, and then like have these modules that you can utilize to define your application and algorithm. And then the hope is that then you can have this flexible multi-backend support for seamlessly, implementing your algorithms on different types of hardware, but mostly it's for Loihi 2 now. And we've been then also just exploring lots of applications and essentially looking at how EDP or other metrics like just the energy and latency go with using the neuromorphic device, and so this plot is kind of describing some different algorithms that we've been looking at. And so we've been looking at nearest neighbor search, or like these optimization algorithms, as well as deep learning. But with the sort of architecture, the kind of conventional feed forward deep learning models aren't really our forte per se. And it's kind of hard to compete with the GPU architectures that are out there. But what really seems to stand out are these new kind of more unconventional, like recurrent algorithms. So there's lots of, especially in computational neuroscience, new algorithms based on recurrent neural networks that seem to have a lot of promise when using this exotic neuromorphic architecture. So that's kind of like the basics of the hardware. And so then what I've been researching lately is using neural inspired algorithms to solve difficult computational problems. And so Carver Mead here is pretty much the founder of the entire field of neuromorphic computing. And he had this insight in the early 90s that, like, what the brain does is really take advantage of the physical properties of neurons, and kind of has these as their elementary physical phenomena. And what's really popular recently is using quantum physics to then try to solve very difficult, combinatorial optimization problems or factoring. And of course, Google is claiming quantum supremacy already, or was years ago, but there was already a lot of backlash to these claims. And it's not really clear that quantum computers can really do everything that they promise. And there's a lot more skepticism about them in general. And so there may be really a issue with scaling up quantum computing. And a lot of what these people kind of point to is just the need for error correction, and how as these systems scale up, the error correction might not be something that can be overcome, and you might not get these really amazing exponential scaling promises that quantum people have been claiming for years. But in computational neuroscience, we've had a long history of kind of thinking about how you can use sort of physics or like biology to solve difficult computational problems. And there's this pretty famous paper in computational neuroscience where we use what we call Hopfield networks or tractor networks to pose these like combinatorial search problems. And so here, this paper by Hopfield and Tank describes how you can use an attractor network and define an energy landscape, and then define the traveling salesman problem with this energy landscape formalism, and then use sort of the gradients and the physics of this recurrent neural network to solve this optimization problem. And so then really the question is then, can we now that we have this neuromorphic computing device, can we actually take these ideas and these algorithms and scale them up? And so this is like where most of my research comes into play. And so what I've been looking at is some different ideas for how to scale up these different algorithms using the mechanisms provided on neuromorphic hardware, as well as like looking at new types of formalisms for programming the hardware and thinking about distributed computing. So that's what vector symbolic architectures or hyperdimensional computing is about a lot. And then we've also been looking at the ability to do these higher order interactions. So typically, if we think about neurons and weights, we just think about like a vector matrix product. But from modern neuroscience, we actually see these other nonlinear phenomena. And so we've been starting to formalize some algorithms that have these higher order multiplicative like connections. And this actually adds a lot of new computational abilities to the potential of neural networks. So in neuroscience, um, one of the more famous observations that we have is from the mouse hippocampus. And so these are recordings from deep in the mouse brain, where basically the mouse is this black line on the left, and he's running through just a box, running around over time. And then every time one of the neurons spikes, they just plot a little red dot. And so what you see are these place cells. So it seems to be that these neurons in the hippocampus are forming some kind of map and representation of the mouse's location in space. And basically then, we've been studying these place fields for years now. And what we also see is that there is this oscillation. So in the hippocampus, there is then this large kind of extracellular oscillation you see called the theta cycle. And then what you also see is that the spikes that these neurons produce are locked to this rhythm. And so you see these rhythmic spike timing patterns inside the mouse's brain. And for years in computational neuroscience, the kind of main paradigm has always been rate coding. So essentially, we think about vectors and numbers in the vectors, and then we just map that onto spikes per second. And it's basically ignoring really the potential of spike timing. But many of the proposals in the field about using spike timing codes have a pretty major flaw, which is that they're quite brittle. So often the timing patterns that conventional some of these other spike timing codes suggest would fall apart quite easily. If there's any jitter in the spike timing, they tend to break. And so then we came up with a proposal, though, of how we can use the oscillatory dynamics along with the spike timing code to make a more robust variation of a spike timing code that can actually be compared to representations in the complex domain. And so basically, like if we think about vectors of complex numbers, then they have amplitude and a phase. And if you have this reference frame, you can actually represent the complex value, the complex phase, as the timing of the spike relative to this background oscillation. And then as well, if you have this complex valued matrix algebra, then you need these complex valued weights. And we showed how actually, like we see in neuroscience, there are synaptic delays, and you can in fact map the phases of complex valued weights also to then synaptic delays. And then there's a direct correspondence between doing complex matrix algebra and using these oscillatory spike timing codes. And then to make it robust, we use the same idea that I showed earlier with the Hopfield and Tank of creating these attractor networks. And so essentially, the idea of the attractor networks is you form an energy landscape, and then the dynamics of the network drive the network state into these local minima. And so we showed in this paper that you can actually do this in the complex domain as well. So you can define the same kind of learning rule and just define these neural dynamics that create an energy landscape, and do this all with complex value numbers. And so then we can take this formalism then of complex valued matrices and vectors and turn it into this spike timing representation and use energy landscapes to then make these very robust spike timing attractor networks. And so here we, excuse me, show a network motif built from this formalism where we use spike timing and synaptic delays to program in different patterns into the energy landscape. And then by initializing the network somewhere close to these patterns, so on the right, you see sort of its dynamics over time, where some images are sort of stored into the network, and then the network is first initialized to like this overlapping image. But the energy landscape dynamics then drives it to one of the local minima, and the system stabilizes and produces this rhythmic spike pattern. So that basically the complex vector just is being represented over and over, but changed into a spike timing code. And then you can build these robust attractor networks using spike timing. So then what we also showed is that you can also use these more exotic neuron models. And if you make actually this simple oscillator neuron called a resonating fire neuron, you can implement these equations even more directly. And so here's just another example of how where we have this oscillatory, intrinsically oscillatory neurons, basically just like a harmonic oscillator, but then it has a spiking mechanism. So then whenever the phase kind of crosses the 0 point and it's above the threshold, the neuron will spike. And so you can implement the same equations using this model, and this is more convenient for implementing it on the hardware. And we also showed in this other paper, you can then use this complex valued formalism to do a bunch of signal processing applications, like just computing spectrograms or computing motion filters, and implement them with these oscillatory dynamics and using spike timing to represent the complex values. So then there is this other large problem about how do you use distributed vectors to represent information. And in neuroscience, there was this conundrum that the conventional connectionists came across called the binding problem. And typically, when we think about how neurons represent information, we like to say that, okay, there's a neuron that represents triangle. There's a neuron that represents square. There's a neuron that represents the up position. There's a neuron that represents the down position, and so on. But what they realize is that then there's this issue where what they call the superposition catastrophe. So often, if you take these representations and add them together, then the connections between the properties of the objects gets lost. So the representation of up triangle and down square is the same as the representation of up square and down triangle. And so this was like a problem that people couldn't figure out how to solve in a nice way for a long time. And this problem is what drove me into studying this framework that we now call vector symbolic architectures, or hyperdimensional computing, where we've developed an operation between vector representations that allows you to represent these bindings as well as kind of the conventional things in connectionism. And the sort of insight about how it works is to use the properties of high dimensional randomized vectors to solve the binding problem in essence. And then over the years, there's been different flavors of these architectures that have been invented sort of in parallel, but more recently, we realized that the geometric properties of these randomized vector representations are kind of the same, and they can be sort of unified and look together as a whole. And so there's a bunch of different implementations, but the simplest one to understand is this bipolar one. And so basically, you just, instead of a neuron representing a symbol, you use an entire randomized vector to represent a symbol. So you pick a vector for your symbol made out of random plus ones and minus ones. And just like in normal connectionism, you use inner products to compare the similarity. So like if you want to know what's being represented, you just do a dot product. And then you have these other operations, though, that allow you to form an algebra over these vectors and create more complicated representations. And namely, there's this binding operation, which in this case is the Hadamard product, or element-wise multiply. And so then what you can do is, if you want to represent a binding, is actually take your randomized vector representations and multiply them together. And in the inner product space, what this means, though, is that since these representations are random, the dot product between two random vectors is very close to zero, or like they're close to being orthogonal. quasi-orthogonal, we call it. And the binding operation sort of preserves this property. So if you take two randomized vectors, do the Hadamard product, then the result will be quasi-orthogonal to the two inputs. And this way you sort of have the ability to create these representations of bindings on the fly. And then basically I'll just mention that there's a complex valued variation of this. So then we can do these complex valued bindings as well. So then what that allows you to do is sort of solve one of these conundrums in connectionism about how to use vectors to do a lot of things you do in conventional computing. And so with the binding operation and the sum operation, you have the ability to now represent data structures in these distributed vectors. And so you can essentially follow this algebraic formalism to then create data structures and then manipulate these vector representations in a way you would do like in a conventional computer to solve problems. And so then in one of our papers, we described then a new framework based on these sparse block codes. And so what's convenient and what to take advantage of the neuromorphic hardware, we want our neural representations to be sparse. So we want to minimize the communication between the neurons, right? But this Hadamard product bipolar representation, of course, every neuron's a +1 or -1. So you have to do a lot of communication in that case. But then we invented like a variation where we break a vector into blocks, and essentially one element of each block is active. And then there's another kind of binding operation that has the same properties. And you're able to do this vector algebra, create data structures, but in a way such that the representation is sparse. And so that's that. And then we've also been developing these ideas about how to represent continuous values. And so we built upon this actually very old idea from Tony Plate of how to represent continuous numbers with complex values. And essentially, by just using these complex numbers and then putting a continuous number in the exponent, we have this flexible continuous binding operation. And so essentially, like, we're just taking these complex phasors and spinning the phases proportional to this continuous number. And what that does is induce a similarity kernel in the vector space. And just recently, we kind of realized that this is connected to this very famous paper, Random Fourier Features. And if you're familiar with like the transformer literature, these position encodings that they use are actually based on this Rahimi and Reck paper. But we show how actually this can be extended using ideas from VSAs. Oops, I wanted to do this one first, but then basically, in this paper, we also show how you can create different kernels, you can extend things into higher dimensions, you can use the whole algebra to create data structures, and you can do things like create different types of manifolds like a circle or a torus, and use these sort of randomized continuous value vector representations. And one thing then we can do is then take something like an image and encode the image into a vector. And then we're able to then manipulate the image using these binding operations. And so in this case, I just encode the image into a vector like so. And then I can apply these binding vectors to translate the image by an arbitrary amount. So this can be even a continuous sub-pixel translation. And then just the Hadamard product just kind of distributes through this representation, and this is a way to then encode an image and manipulate it in the vector space. And you can even then create the vector representation in ways such that the image is like a torus in this case. So the things being translated kind of wrap around the sides of the image. So, but then we while studying vector symbolic architectures, realized there's this interesting problem that kind of comes up a lot, and the idea is basically that we have these representations of products, and so here the idea is like you get this vector S, and you know it's actually the combination of X, Y, and Z, but you don't know exactly which X, Y, and Z. So say there's like 100 possibilities for X and Y and Z, and then essentially then S has like 1,000,000 possible combinations to search over to figure out what its components are. And you kind of know like the set of possibilities, but you don't know the particular one. And so then this leads us to this problem we face a lot, which is just like this combinatoric search and doing this factorization problem. And so we've come up with this new recurrent neural network architecture for solving these factorization problems. Basically, the idea is you can use these vectors to represent in superposition many guesses for each of the factors, and then sort of do this noisy inference to tell like what the other factors are. And then by using this like cleanup memory dynamics, you can then refine this guess. And if you iterate through this process over and over, we found that this network can solve these factorization problems. And so then basically the dynamics sort of looks like this. So we pose this problem with 1,000,000 combinations to search over, and the network sort of ran like, so then time is going down here, and this is like each of the factors that the network is trying to represent. And so it sort of does this stochastic search, and then suddenly it like has a moment of insight where it realizes there's this particular combination of factors, explains the vector very well, and then it comes into a stable fixed point. And so then we characterize the network and show that actually it can outperform these conventional optimization systems, and it has this what we call its operational capacity. So depending, we can scale the network up to arbitrary size, and depending on the number of combinations that the problem has and the scale of the network, we sort of empirically guarantee that it will find the solution. This has just led us to then like be able to define these generative models and define like these perception problems as actually factorization problems. And so basically the idea is that like in a scene, a very simple scene like this, we can represent objects as their shape and their location and their color as different factors. And then the entire scene is like a set of these objects. And this is like just a generative model way of describing scenes. And then essentially we can formulate these problems in a way that they're vector factorization problems and plug them into this resonator network. And essentially then what the network does will sort of hone in to one of the letters and break it up into its generative factors. And so this is something we think is a new way of like really tackling these perceptual problems. And then we've also expanded this to do visual odometry. So essentially, the idea here is that there's some transformation being applied to the camera, and you have this internal representation or in this internal map, and you want to factor out the transformation that maps your current input onto this internalized map. And this is basically SLAM. And so then we show how you can use, again, this resonator network architecture to solve the plant SLAM problem and localize the camera view onto your internal representation of the map. And and then, yeah, I guess very quickly, we also just explain how actually doing semi-prime factorization can also be expressed as this vector factorization problem. And so, of course, semi-prime factorization is, core to cryptographic algorithms, and but then you can again use these ideas of the resonator network and this complex numbered algebra to effectively express semi-primes in these vector representations. And then you see that then the semi-prime is really the product of its prime factors. And then you can use the resonator network to then just solve this semi-prime factorization problem. And so we've been basically just characterizing this possibility and trying to make it amenable to neuromorphic hardware. Yeah, so then basically what I've been researching lately is just how to put all these ideas together to scale up these different types of recurrent physics-based algorithms on the neuromorphic chip, developing new types of neuron models, as well as these new types of sparse vector algebra operations, and just trying to implement this on the chip. And then one other just proof of principle thing I've been working on too is just to also do dynamic simulations. So like, again, because like recurrent types of networks are pretty good on the chip, I've been looking into just doing fluid dynamics and implementing essentially these Navier-Stokes equations on the neuromorphic architecture. And so this I just mentioned as just a first step into maybe doing also physics simulations on the hardware as well. So then, yeah, that's basically my talk. Thanks everyone for paying attention, and thanks for having me. And I guess I'll take questions now.
Thank you so much, Paxon. So first, we're going to take a couple of questions from the room and then see who has their hand up on Zoom. So any burning questions to start with? Okay.
Hi, thanks for the nice talk. So I was wondering if there are any lessons for hardware development from large language models. So basically, do you anticipate that there's certain processing capabilities that are emergent as you scale up the system beyond a certain size? And unless you do that, then you can't really do the kind of processing that you intend. So this same thing happened with finite element analysis when it first started, right? So people didn't believe it would be useful for anything until there were, very large grids.
Yes. Okay. So yeah, the question is about large language models and scaling. And so we're actively working on this. This February, everyone at Intel, freaked out and was like, oh gosh, we need to think about how to do large language models. And so then we've been looking into the various different ways of implementing them. And one of the things that the large language models have is also this multiplicative second order operation. And so it's very similar to this binding operation I was telling you about. And so we have the ability to implement that type of thing on the neuromorphic hardware. And then the other kind of idea is actually to make it more recurrent. So the kind of conventional ChatGPT is stacked over and over these layers of these key value queries. But then there's a couple of people researching then ways to just make this through a recurrent loop, right? So then that way you don't need quite as much memory. And then also that has, more promise for the architecture. But we're also actively, re-engineering the chip to kind of think about how to do the large language models more efficiently as well.
Great. Anyone else in the room? Okay. Oh, there's one over there.
Thank you for the talk. I didn't quite get what was the main driver that allowed you to reduce the power so much in this new approach. So could you say a little bit more about why these chips use so much less power than the previous generation?
Yes, the main thing that reduces the power is, well, there's a couple things. I guess it's asynchronous. So there's no global clock. So there's not like a big clock coursing through the chip. And the other thing is that the memory and the computer co-localized. And so then just those two things alone. I mean, we also, lower the voltage and do these other things. It's all the representations are fixed point, and there's only a limited instruction set. So there's a lot of these other little tricks with the asynchronous stuff that I'm not too familiar with, but yeah, mostly it's about the no clock and the co-localization of the compute.
Great. Anyone on Zoom? Okay, I have one question very quickly. So on slide sort of 24, 25 or so, you were talking about this threshold this representation with polarization and these waves that you observe in like mouse brains and stuff. How do you go about taking something that complex and translating it for something like Loihi, which has this sort of sparse, limited representation in these information packets? How do you implement that sort of global oscillatory behavior?
Well, right, yeah. So the formalism of connecting the spike timing codes with complex numbers allows you to just change it into math, and then the whole VSA architectures gives you an algebra that you can then follow to build more complicated algorithms, essentially. And so it's really the ability to formalize the oscillations and the spikes into this math that allows you to build complicated networks. But then we show like the mechanisms. You can have different types of mechanisms as well. So then using these like intrinsically oscillatory neurons sort of induces the wave. And this is a very efficient way to do it on the hardware. But we show also that there's more like biologically inspired ways of doing it as well, where you can use the network dynamics to induce the oscillation. And then by kind of using the attractor and the robust idea, all that complicated biophysics can then be abstracted in a robust way to mathematics, and then kind of using the mathematics to build complicated algorithms.
Okay, last chance on Zoom. Otherwise, I'm going to ask one final question, unless there's another one from the room. Okay, I had an experience with a competitor's neuromorphic chip a few years ago, and one of the things we were missing from it was the ability to do online learning, so online backpropagation. Is Loihi able to do this?
Yes. So yes, Loihi has an entire formalism for doing synaptic plasticity. And there is essentially a lot of inspiration from computational neuroscience of doing spike timing dependent plasticity. But the whole framework goes beyond that. So there's this essentially programmable engine that allows you to, express these like spike timing dependent plasticity mechanisms. But also then you can add in what we call three-factor learning, where you can do basically the error signal as a third factor along with the Hebbian plasticity to essentially do backpropagation. And so we have an entire library based on doing backpropagation. And there's also this issue with the discontinuity of the spike, but people solve this with what we call surrogate gradients. So sort of just kind of approximating the gradient over the discontinuity to like allow for the backpropagation.
And one more, and then we do have to leave because there's a follow-up talk in here.
Follow-up. So do you train on chip, or do you train offline and then upload the weights?
Yeah, we mostly do both. A lot of our current application examples are just trained offline, and then we port it over to the chip. But it was a long software engineering effort to enable the plasticity rules. But now we have like one-trip training. We have these examples of continual learning where you can sort of update the things on the fly and use the learning engine on the chip.
Okay, thank you so much. Let's thank our speaker again.